We spent a lot of time talking about covalent compounds and how those, um, how they're shaped, what the bonds are like, but we haven't actually talked about why bonding happens. So today is, I've kind of done this chapter in the reverse order, all right? We've done the practical stuff first because I think it needs a little bit more practice, and now we're going to do a little bit more of the background information, all right? So today is the introduction to bonding. And the question is, why do chemical bonds form? Well, in a word, it's energy. Remember, everything is always trying to minimize its energy. Okay? A lower energy is more stable. So kind of keep in mind, like dropping a book off a table. It's lower energy on the floor than it is on the table. So it'll fall to lower its energy. When you have two atoms far apart, they're not really interacting with each other. But as they get closer, they can start to interact. And this interaction will actually decrease both of their potential energies. So you see here's a graph of potential energy versus distance between the nuclei. All right? And so you can see when they're far apart, there's basically no interaction. But as the two things move closer together, they start to interact with each other. And the question is, how do they interact with each other? What's causing this interaction? Well, you should kind of have an inkling for this, right? Let's talk about the type of interactions that there can be between two atoms. All right? Well, how about the subatomic particles involved? Well, I could have an electron-electron interaction. Okay, would that be a repulsive force or an attractive force? Well, that would be a repulsive force. Okay, now would that increase potential energy or decrease potential energy? Well, if these two electrons are repelling each other and you're forcing them close together, that would increase their potential energy. They don't want it. The electrons don't really want to be close to each other. All right, well, so that doesn't really tell us anything because we haven't, I mean, these are repelling each other. So why would a bond form? Well, let's move on. How about proton-proton? Well, proton-proton interactions will also be repulsive, which means that they would also increase potential energy. Oh. What? So what are holding atoms together in bonds? Well, it's the last set, right? A proton interacting with an electron. So now we have opposite charges, so those are going to attract each other. Okay? And because we're attracting each other, they're going to be lowering potential energy. Because those two things sort of, quote unquote, want to be close together. So we have these two forces here that are increasing potential energy, these two interactions, and then we have this interaction which is lowering potential energy, and it's sort of the balance. Now, if we go back to the simulation here, you'll notice that if the atoms get too close together, there's actually a huge increase in potential energy because now the positive interactions from the nuclei increase, okay? There's sort of a balance where you're balancing all of these. And when you get a perfect balance, that's when a bond forms. Okay? So you know that two helium atoms don't interact or don't form bonds. Well, what about, this is now hydrogen, okay? When hydrogen gets close together, you'll see the electron clouds start to overlap each other. And we know that that's what happens when a bond is formed. Okay, so I'm going to have them collide with something else so that they lose a bit of energy. Okay, now they lose a little bit of energy and now they're stuck. Okay, they're stuck at the bottom of this energy well. And at the bottom of this energy well is where a bond is formed. Okay, Now, if I compare the helium potential energy versus the hydrogen potential energy, you'll notice that there's a huge difference in energy. And that shouldn't be surprising because hydrogen atoms actually want to interact with each other. They want to form a bond. Helium is a noble gas, and it doesn't want to form a bond because it's stable, okay? It has its filled octet. All right? So just to kind of show this again, the distance between the nuclei here, hydrogen nuclei, versus the potential energy. Far apart, there's no interaction. It's basically zero. And then as they move together, they start to interact. And out here, you know, you're starting to get the proton-electron interactions. And then you reach this point down here. And this point down here is what we call a chemical bond. Right? And so this chemical bond, when this chemical bond forms, the distance between the hydrogen nuclei, we call that the bond distance. Okay? And the energy from infinitely far apart down to this this minimum here is what we call bond energy. And that's going to be the average bond energy. Now notice that you might have some molecules that are here, you might have some molecules that are here. There's going to be a sort of continuum. And right at the bottom here is going to be the average bond energy. Okay, so let's look at some bond energies and bond distances. Okay, I show you this table. It's really easy to see the trends, right? No, because you wouldn't look at a table for a trend, right? What would you do? You graph the information. So here I have graphed this chart, okay? And you'll notice that this is basically a straight line. There's basically a linear correlation. It's a negative correlation, but there's a linear correlation between these two things, okay? Now, there is one set of outliers here, right down here. And this is actually two interactions. This is nitrogen-nitrogen and fluorine-fluorine. Okay, so that's just some stuff to keep in mind, all right? As bond length increases, bond energy decreases. And bond energy is just defined as the energy you would have to put in to break a bond. That's why it's negative here, but it's positive here, because it's how much energy you would have to put in to go back to both atoms being infinitely far apart. Okay, so you're breaking bonds. So you can see generally that a longer bond is a weaker bond. Okay, well, what about single and multiple covalent bonds? Now, we've talked about this, right? I kind of said, you know, when we were talking about resonance, that a double bond is shorter and has a higher bond energy because you're sharing 4 electrons rather than 2 electrons, all right? So they're held tighter, and you'd have to put more energy in to break the interaction. All right. So another thing that we need to kind of clear up here is we've been talking about all covalent bonds, and I've just been sort of whitewashing everything as like, well, we'll talk about covalent and ionic later. This is just covalent. Now, that doesn't actually always end up being true, okay? And hopefully you saw this chart here, and as it turns out, bonding is really just this sort of continuum, okay? And the reason that there's this continuum is the idea of electronegativity. And if you need to pause and go look in your notes to remember what electronegativity is, now might be a good time to review that a little bit. Okay? So for example, if I took a bond like HF, okay? Now, the other way of representing that is showing these 2 electrons being shared between the fluorine and the hydrogen. Now, there is a big difference in electronegativity between hydrogen and fluorine. Okay? So, as it turns out, fluorine basically takes these electrons and holds them tightly. And hydrogen is kind of okay with giving them up. So rather than looking like this, what it actually looks like is this. Okay? Where most of the electrons are sitting on the fluorine. Okay? Now, if you compare that to a ionic bond, something like Na and Cl, what we know is that, if we remember way back to the beginning of this unit, okay, chlorine's got 7 valence electrons, sodium has 1. Sodium wants to give up its electron to chlorine to make sodium plus and chlorine minus. Okay? So you can see that these are actually kind of similar things, all right? Now, we still would call this bond covalent. We just call it polar covalent. Okay? There's polar covalent, and there's nonpolar covalent, and there's ionic, all right? Ionic is a give and take of electrons, and polar covalent and covalent are a sharing of electrons. Now, polar covalent's an uneven sharing of electrons, and nonpolar covalent is an even sharing of electrons. So if we compare something like carbon and hydrogen, so this is 0.4, so that's right around in here. Okay, it's kind of in the transition between nonpolar and polar covalent, but we always consider this a nonpolar covalent bond. So that's a nonpolar covalent bond. And the more negative atom, well, it's the carbon, okay, even though there's a small difference in electronegativity. And remember that the trend looks something like this. Trend looks something like this. So what about something like carbon and sulfur? Well, as it turns out, the difference in electronegativity is 0, which means that this is a nonpolar covalent bond, and there's no more electronegative atom. And in your textbook, there is a page, there's a table in your textbook that has all the electronegativities, so you can compare all these things, all right? Here, I'll bring this up. Well, oxygen and hydrogen, well, the difference here is 1.4. Okay, well, 1.4 is pretty squarely in the polar covalent bond. So this is a polar covalent bond, and the more electronegative atom is oxygen. Sodium and chlorine. Now we're up here, okay? We're up in the ionic region. So this is ionic. And this is, the more negative atom is chlorine. And the last one, cesium and sulfur, that's another ionic, and the more electronegative is sulfur. Okay, the more negative atom is sulfur. Okay, so that's sort of just showing you the difference. Now, we've talked a lot about covalent bonds and polar covalent bonds. Today, we want to focus a little bit more on ionic bonds. Okay, and one of the first things to keep in mind is that the chemical formula for an ionic compound, something like, say, sodium chloride versus, let's say, HCl. Okay, so sodium chloride versus HCl. And this is, okay, well, we're not going to worry about names right now. So sodium chloride, this is an ionic compound. And ionic compounds actually, because the sodium gives up its electron, what happens is you end up forming these large crystals, which we're going to talk about in a minute. Whereas in a covalent bond, they're sharing electrons. So the two things are sort of physically attached to each other. okay? Which means that a chemical formula for an ionic compound represents something a little different. It's the simplest ratio of the compound's combined ions that gives electrical neutrality. Okay, so let's give electron dot structures for potassium and chlorine. Okay, so if we go look at the periodic table for potassium, we know that that wants to give up one electron. It has one valence electron. Okay, so that's going to be potassium with one valence electron, and chlorine has 7 valence electrons, right? Cl has 7 valence electrons. And since I can look at this and I can say, all right, well, there's a big difference in electronegativities here. So this is going to be an ionic bond. So I can say that rather than sharing, what's going to happen is the potassium is going to give up its valence electron so that it has an octet now. Okay, it would be isoelectric with argon, and chlorine would want to gain one electron to be isoelectric with argon. Okay, so you give up this electron and you form K plus and Cl minus with all the electrons around it. And this is your ionic compound. Now compare this with magnesium and chlorine. So magnesium has 2 valence electrons. Let me move this down just a little bit. And chlorine has 7. Uh-oh. Okay, well, we know that magnesium is going to want to give up one of its electrons, but now what? Okay, chlorine's happy. It can't accept another electron, but magnesium is still unhappy. Well, remember that this doesn't happen with, like, single molecules. There are, 10 to the 26th, 10 to the 23rd, of these atoms present. So you can have a second chlorine atom that would accept the electron-fed magnesium. Okay, so now magnesium would be losing 2 electrons, which means it would form Mg2 plus, and you'd have 2 chlorine negatively charged chlorine atoms. Okay, we can do another chlorine atom here. Or another way to write this would be Mg2 plus 2 chloride Cl minus ions. Okay. Well, what about calcium and sulfur? Why don't you pause and see if you can do this one on your own? Here are my 2 calciums. Calcium has 2 valence electrons. Okay, and sulfur has 7 valence electrons. So now, that's just straightforward, okay? We share 1 electron here, we share 1 electron here, we get Ca2 plus S2 minus. All right? So the chemical formula for this would be CaS. The chemical formula for this would be MgCl2. And the chemical formula for this top one would just be KCl. All right? Because the chemical formula for these represents the simplest ratio of the ions. All right. So because we've given up, so for example, because calcium has given up its electrons, ionic compounds have some pretty interesting properties. And one of them is that they form these huge three-dimensional structures called crystal lattices. Okay, so the positively charged ions and negatively charged ions arrange themselves in a uniform pattern in order to maximize the negative or the positive interactions, so like the plus minus interaction, and minimize the bad interactions like plus plus or minus minus. So if we say here's a chloride ion, right? So this chloride ion is going to be close to this sodium ion, this sodium ion, this sodium ion, this sodium ion, this sodium ion. There'd be another one on top, right? So that would maximize the number of positively charged atoms around, or ions around, that negatively charged ion. And you can see that the Cl minus are going to, the negative interactions are going to be a little further away because they're opposite each other in this little square. All right. Another so the way that the strength of ionic compounds is measured is lattice energies. And what lattice energy is just defined as, it's the amount of energy that's released when 1 mole of crystal lattice forms. Okay, so when 1 mole of all these ions come together, they become more stable, so they release a bunch of energy because you have to have conservation of energy. All right, so they'll release a bunch of energy. So, for example, lattice energy of sodium chloride, it releases negative 787.5 kilojoules per mole. That's a huge number, okay? Which means that sodium chloride is actually very stable. And if I take this idea and I now compare melting point and boiling point for ionic compounds versus covalent compounds, now the difference becomes very clear, okay? So in order to melt, for instance, a ionic compound, you'd have to break up the lattice energy. All right, so you'd have to put in a bunch of energy, which means that ionic compounds have huge boiling point or melting points. Look at this. This is melting point. Sodium chloride, 801 degrees, versus let's say HF, negative 83 degrees Celsius. Huge difference. So the interactions between molecules in covalent compounds is much weaker than the interactions between ions in a crystal lattice. Okay, they're just very strong. Now, one of the weird things about crystal lattices is that if you hit them, they will shatter. Okay, so here's like a side look at a crystal lattice, and you've got all these positive interactions. Positive meaning they decrease energy. They're attractive interactions. Okay, what happens if I now like use a hammer and hit this row of atoms up, and I shift them up 1? Now, instead of being attractive forces, there are a bunch of repulsive forces, so they'll break apart. Okay, so that's why you can shatter ionic crystals. And so that's basically it. I also had you do some reading on metallic bonding. All you really need to remember there is C of electrons. Okay? Bring your questions to class and we'll answer them.